Hello and welcome to helpyourmath.com. In this video, we're going to look at simplified forms of radicals with numerical and variable radicands. Before we look at examples, let's just review a few things. What does it mean for a radical expression to be in simplest form? If n is the index, it is when the radicand has no perfect powers of n factors besides 1. So for the numerical part, we would look for perfect powers of n factors. So if we have the square root of, let's say, 8, are there any factors of 8 that are perfect squares? And the answer is yes, because we could rewrite 8 as 4 times 2, where 4 is a perfect factor, a perfect square. So then what we could say is we could rewrite 8 as 4 times 2, and then we would take the square root of 4, which is 2, and multiply it to the remaining factors that weren't perfect squares and have no perfect square factors. So the square root of 8 we say is simplified when it's written as 2 times the square root of 2. The same would be true if we had a different index, like if we had, for example, the cubed root of, let's look at the cubed root of 54. So we would be looking for perfect cubes. And does 54 have any factors that are perfect cubes? And the answer is yes, because 27 is a perfect cube and 54 is 27 times 2. So what we would do is we would say, okay, well, we can take the cubed root of 27. The cubed root of 2 is not rational, so it would just stay the cubed root of 2. The cubed root of 27 is 3, so we'd write this as 3 times the cubed root of 2. That's if we're looking at the numerical part. If we're looking, I'm going to erase this so we can read the next part. If we're looking at the variable part, we look for the largest multiple of the index smaller than or equal to the exponent of the variable. So what does that mean? If we have the square root of x to the 15th, so this is the square root, the index is 2 even though we don't see it. So what multiple of 2 is as close to 15 as possible without going over? That would be x to the 14th times x to the first. Then we can take the square root of x to the 14th. X to the 14th is a perfect square, and its square root is x to the 7th. So this would be x to the 7th times what would be left under here would be just one factor of x. For this example, and for all examples in this video, we are assuming that all variables represent positive values. So x is a positive value. We're not going to worry about if they're negative and what we would have to do there. So you see what we do? We find the largest multiple we can that's under or equal to the given exponent, and then we can take the root by dividing by the index. If we're looking at a cube root, so if we have the cube root of x to the 17th, well, what's the largest multiple of 3 that's under 17? That would be 15. So we would write this as x to the 15th times x squared, right? Because if we add those exponents, that would get us back to x to the 17th. Then we can actually take the cube root of x to the 15th because x to the 15th is a perfect cube. And this cubed root of x squared would just stay the cubed root of x squared. The cubed root of x to the 15th would be x to the 5th, right? We would divide 15 by 3. And this would be multiplied to what's left under the radical, the cubed root of x squared. Notice that when we are dealing with cubed roots, we keep that index throughout. It's really easy to just forget about it, but if you forget about it and you don't include an index, you are changing that cubed root to a square root, which is different and therefore wrong, so just be really careful about that. And as I mentioned, we're going to assume that all variables represent non-negative real numbers. Okay, let's get started. So we have the cubed root of negative 0.0064 divided by 2. Now, what we could do, what I actually like to do is I actually prefer dealing with fractions rather than decimals when it comes to radicals. So I'm actually going to rewrite this as a fraction. And this would be equal to the cubed root of negative 64 over 1,000, because that's 64 thousandths, divided by 2. Then we can work each part separately. So I'm going to separate and write this as 2 separate cubed roots. I'm going to look at the cubed root of negative 64 divided by the cubed root of 1,000, all divided by 2. Notice that when I split them up, I only include the negative one time. We only include the negative once. You can either put it with the numerator or the denominator, but it's wrong to include it with both. And the reason it would be wrong to include it with both is because then actually that number would be positive, because a negative divided by negative is a positive. Okay, let's get started. The cubed root of negative 64. So is negative 64 a perfect cube? Oh, it is. Yeah, it's 4. or negative 4 actually. So we would write this as negative 4 over, and then how about 1,000? Is 1,000 a perfect cube? It is, and its cubed root is 10. So we would have negative 4 over 10 divided by 2. There's a lot going on here. If you want to go back to the decimal, you can. If you want to rewrite this with the little division sign, that might be nice as well. So we'll do that. So it's negative 4 over 10 divided by 2. Now, how do we divide with fractions? First, we're going to write 2 as a fraction, 2 over 1. And then we're going to rewrite the division as multiplication by multiplying by its reciprocal. So this is going to be negative 4 over 10 times 1 over 2. And now can we simplify before we multiply? Yes, we can. 2 goes into itself once, and it goes into 4 twice. Now, we could simplify this further, but I'm actually not going to. Why am I not going to? Because the question was given as a decimal. Well, I guess it was given as a decimal and a fraction, but it's customary you want to keep it the way that it was given. And since I see the decimal first, I want to write this answer as a decimal. Now, why wouldn't I simplify further if I'm writing as a decimal? Because if we look at what we have left, negative 2 over 10, this is decimal form. This is negative 2/10, negative 0.2. So I would write my answer like this, negative 0.2. If your instructor is okay with you leaving it as a fraction, that I would simplify it down to negative 1/5. So negative 1/5 and negative 2/10 give us the same result, both of which are when we simplify that particular radical expression. How about our next example? So in this example, we want the cubed root of 24a cubed b squared c to the 5th. Remember that the numerical factors, we treat them differently than the variable factors. For the numerical factor, we want to find a perfect cube factor. What's a perfect cube that's also a factor of 28? Can you think of one? I can think of 8. So we can think of 24 as 8 times 3. This would be the cubed root of 8 times the cubed root of 3. The cubed root of 8 is 2, and the cubed root of 3 is the cubed root of 3. So what I'm going to do is I'm going to put the 2 here, and I'm going to set up my radical over here, because I think I'm going to be able to pull some of the variables out as well. So far what's left under the radical is the 3. Okay, so that was the 24. We simplified the cubed root of 24. Now we need to simplify the cubed root of a cubed. Well, the cubed root of a cubed, wait a minute. Oh, wait, the cubed root of a cubed is just going to be a outside the radical, so we can pull out an a, and that works out super nice. Yay! How about the b squared? The cubed root of b squared? Well, unfortunately, b squared, the exponent, is smaller than the index. We're not going to be able to simplify the b at all. So the b squared is stuck under the radical. There's no factors of a remaining under the radical because it was a perfect cube. How about c to the 5th? So we do have a perfect cube factor in c to the 5th. The largest multiple of 3 that we can get is 3 itself. So we're going to rewrite c to the 5th, or think about c to the 5th as c cubed times c squared. We can take the cubed root of c cubed, right? The cubed root of c cubed is c, and then the c squared will be stuck under the radical. So our final simplified answer will be 2 times a times c times the cubed root of 3 times b squared times c squared. And you can always do a quick check because these exponents should be smaller than the index, right? If we have something that's bigger than the index, then we didn't simplify enough, and we would need to keep going. But this would be our final simplified version for this example. Okay, this example looks the same. What's different? The index is different. So this time we're looking at the square root. So now we have to shift gears here. We're looking for perfect squares, starting with 24. So we can think about everything separately. The square root of 24. What is a perfect square factor of 24? Can you think of one? Well, let's see, 4. Yeah, 4 goes into 24. 9 doesn't. 16 is too big, so 4 it is. So we can think about 24 as 4 times 6. Now notice that I'm picking different factors here because this time we're looking for perfect squares, whereas in the previous example we were looking for perfect cubes. Let's see, the square root of 4 is 2, and then the square root of 6 is going to stay root 6. So I'm going to set up my radical. I have 2 outside the radical from the square root of 4, and I have that 6 stuck under the radical. Okay, moving on to my a cubed. So the square root of a cubed is not a perfect square, but it does have a perfect square factor. We're talking about an index of 2, so we want to write a as a to some multiple of 2, and then a times whatever's left over. the largest multiple of 2 we're going to get is a squared, and it would be a squared times a to the first. So we can take the square root of a squared, the square root of a squared for this example, because we're assuming a is non-negative, which would be a. So this becomes a. This a that's stuck under the radical remains stuck under the radical. Next we have the square root of b squared. The square root of b squared is equal to b. b is out of the radical, so it's going to join the 2 and the a that are out of the radical. C to the fifth. So we want to think about c to the fifth. We want to figure out a perfect square factor that's not as that would go into c to the fifth. The largest one that we can come up with would be, what's the largest multiple of 2 that's under 5? That would be 4. So we would think about this as c to the fourth times c to the first. And the square root of c to the fourth would be c squared out of the radical. This c to the first is left under the radical, and we don't need to include that exponent of 1. So we would say it's 2 times a times b times c squared times the square root of 6ac, what was left under the radical. And that would be our final simplified answer. Okay, for our next example, as always, I suggest you pause the video and try this one on your own to see how you do. How'd it go? Well, we're dealing with a square root, which means our index is 2. And we want to split up. I like doing everything separate. So I'm going to start with the square root of 32. So for 32, for the number, what is the largest perfect square that goes into 32? That's a factor of 32. And that would be 16. Now, if you came up with 4 instead, that's fine. But then you would need to simplify the 8 as well, since 8 still has a perfect square factor. So 32 is 16 times 2. And then the square root of 16 is 4. And the square root of 2, we're going to leave the square root of 2. So this is going to simplify. We have a 4 out of the radical, and left under the radical is a 2. For a to the 7th, we want to think about what's the largest. In this case, this is a variable, so we're thinking about multiples. What's the largest multiple of 2 that's not bigger than 7? That would be 6. So we're going to write this as a to the 6th times a to the 1, right? Because that's what the same base multiplication property tells us, is that we can split up 7 into 6 and 1, right, with 2 of the same base, because if we were to combine these, we would add them and get back to 7. The square root of a to the 6th, remember how we do this? We take the exponent and we divide it by the index. So that'd be 6 over 2, which is 3. And the square root of a is going to remain the square root of a. So joining the 4 outside the radical will be a cubed. Left under the radical will be 1 factor of a. For b to the 10th, well, b to the 10th, 10 is a multiple of 2. So we don't need to split it up. We can leave it like this, or we can say that b to the 10th is a perfect square, and its square root is b to the 5th, right? So we would take the 10, we would divide it by 2, giving us b to the 5th. b to the 5th joins our 4 and a cubed. And lastly, we have c cubed. So c cubed is not a perfect square, but it does have a perfect square factor. We can rewrite c cubed as c squared times c to the first. The square root of c squared is c, and the square root of c, we'll just leave the square root of c. So c comes out of the radical, and 1c remains in the radical. Just double checking, we're left with a 2 under the radical, no perfect square factors besides 1. A is not a perfect square, and c is not a perfect square, so I feel pretty good that this is the complete simplified answer. All right, we're almost dealing with the same radicand here, but the index is different, and actually this is the negative of the previous example. So again, I encourage you pause the video and see how you do. Okay, so what I would do is split this up, starting with the negative 32. So negative 32 is a perfect power of 5. It is actually negative 2 to the 5th, so the entire thing will come out of the radical, giving us negative 2. So this would be negative 2 out of the radical. So far, we don't need a radical. Let's see, the 5th root of a to the 7th. So what we want to think about is a multiple of 5 that is under 7, and that would be, well, 5 itself. And what would be left? We would have a squared. The 5th root of a to the 5th, the 5th root and the 5 would cancel, leaving us with an a here. And then we have a 5th root of a squared left under the radical. So it looks like we are going to need a radical after all. Here we're going to have a, and then we're going to have a 5th root of a squared. Always important, I mentioned this before, don't forget to put the index in your radical. If you don't put an index, it's assumed to be a square root. That's not what we're working with here. Okay, next we have b to the 10th, the 5th root of b to the 10th. Well, it turns out that b to the 10th is a perfect power of 5, and it would be b squared to the 5th. So b squared comes out of the radical. We have no factors of b remaining under the radical. And lastly, we have c cubed, the fifth root of c cubed. There are no positive multiples of 5 that go into 3. So we would just leave c cubed under the radical. And our simplified version of this particular problem would be -2 times a times b squared times the fifth root of a squared times c cubed. We can double check our work because 2 is less than 5, so we know we don't have any perfect powers of 5 here. 3 is less than 5, so we can again justify, should be good to go. Last example. Okay, we already have a coefficient, so anything that comes out of the radical is going to get multiplied to what's already there. We are talking about a fourth root, and we don't have to worry about simplifying this. Even if we're not looking at simplifying that's not under a radical, we only focus on the radical. So we're going to start with the 162. And I'm going to go way over here and give myself plenty of room. So the fourth root of 162, we're looking for perfect powers of 4 that are factors of 162. So perfect powers of 4, we might want to write these down because we haven't seen these. We have 1, 2 to the fourth is 16, 3 to the fourth is 81, 4 to the fourth is 256. So basically the question is either 16 or 81 a factor of 162? And the answer is yes, 81 is. Yay, ding, 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 ding. So we're going to rewrite this as the fourth root of 81 times the fourth root of 2. Because it turns out 162 is 81 times 2. The fourth root of 81 is 3. And the fourth root of 2 we're going to leave as the fourth root of 2. So remember what's happening here. This 3 is joining the coefficient that's already there. So it's joining the 2 by multiplication. This comes out and it turns into multiplication. Everything here is multiplication. We're going to multiply 3 times 2. That's going to give us 6. Under the radical, we have a fourth root of 2 so far. Let's see what's going to join the 6 outside the radical. X to the 15th. So we're looking for a multiple of 4 that is smaller than or equal to 15. That would be x to the 12th is the largest one we can get. And that would be 12 plus 3 would give us the 15. The fourth root of x to the 12th would be x cubed. And that x cubed would be out of the radical. This x cubed would remain under the radical. This x cubed that popped out of the radical is joining this x here. This x has an exponent of 1. So we have 1 factor of x, and we have 3 more, giving us a total of 4 factors of x outside the radical. We still have 3 factors of x remaining under the radical. And lastly, the y, we have the fourth root of y to the 6th. What's the largest multiple of 4 that is smaller than or equal to 6? That would be 4 itself. So we're going to say y to the 4th times y squared, fourth root of each of these. The fourth root of y to the 4th, we're assuming y is positive or non-negative anyway, so this would be y. And here we're going to just leave this the fourth root of y squared. So a y comes out of the radical, joining the 2 y's that are already here. We're adding another y, well, we're multiplying another y. Y squared times y is y cubed. So we have a y cubed out of the radical and a y squared left under the radical. Just checking the radicand, 2 has no perfect square factors besides 1. X cubed, nope, y squared, good to go. So I feel pretty good that we successfully simplified this radical. These have been examples of simplifying radicals. Thank you for stopping by.